Welcome, everyone. Please let me know if you can hear me and see me. Please thumbs up or just send in the chat, please. Okay, perfect. So welcome to our first live session of the year at Phantom High Speed. Please share in the chat where you are located. My name is Maria Alvarado. I'm the marketing manager for Phantom High Speed. I'm based in New Jersey. Please share in the chat where are you located. Okay, today's topic is high-speed imaging in aerospace. We have an incredible team from the Ohio State University who will guide us through their research on welding in space, along with one of the applications engineers. Please welcome to our keynote speakers who will introduce themselves before we begin the session. Dr. Antonio Ramirez, welcome. Thank you for joining us today.
Hey, thank you, Maria, and thank you, Phantom Ametech, for inviting us. Let me go ahead and share my screen.
Right.
Let me get prepared here. We're good. So first, let me introduce myself. My name is Antonio Ramirez. I'm a professor of welding metallurgy and additive manufacturing at the welding engineering program at the Ohio State University. And I've been leading this welding in space program at Ohio State for the last 4 to 5 years. I literally lose track of it. So let me get started. So it's myself and two of my colleagues, Dr. Kaue Riffel and a first-year student in engineering at Ohio State, John Cicenas, are going to be presenting for you. So this work has been in collaboration with NASA, the Air Force, Research Lab, and many other organizations. So let me move in here. Before I start, I give all the people the due credit. Not everybody's here. I have a slide at the end that has a lot more names. But this is a big program involving many different companies and organizations. I'm not going to go in detail. As I mentioned, AFRL and NASA, several branches of NASA, Air Force Midwest Hub has funding us, as well as the Ohio Federal Research Network, together with NASA. We also have people from Central State University working with us. Lincoln Electric, NanoRacks, Voyager has been working with us as well. And there are many other professors and people at Ohio State that has been involved in this work. So let me move forward and explain you why we need to do welding in space. The reason we need to do welding in space is because we have needs on space that we cannot fulfill just launching systems from Earth. We need to build very large structures like these reflectors or antennas on space to capture sun energy, convert, and either radiate to air or use on space itself. These are several football field size structures. Not everything can be like unfolded on space. It's complex to do that. We also have a big industry growing now that is doing maintenance and service of satellites or repurposing satellites on space. And at some point, like any place where you go to get your car fixed, the guy will have a welding machine on there. He doesn't use it every day, but when he needs it, he has it and he uses it. So that's what we're developing. Also, space mining is an idea that is being developed and it may grow. And at some point, they need to fix a stuff or build a stuff in space, we'll be ready. And finally, we are talking very seriously as a country that we are going to be colonizing the moon first and Mars, and therefore they are going to need this as well over there. Okay, so why caring about like doing research or welding in space? Because when you move to space, there are three main things that change: gravity, the atmosphere, and the temperature. You go from what we know on Earth, and depends on where you go, you can have, in general, very low pressures or vacuum when you are in deep space or low orbit. Then you can have different gravities. At the moon is 0.2 G, at Mars 0.4 G, and Earth is 1 G. So that tells you like 40% of the gravity on Earth, 20% of the gravity on Earth. Gravity or depends on where you are, very low gravity. That said, temperatures could be extreme as well. When you are, for example, a low orbit, you can be something like 295 Kelvin when you are inside the habitat, but if you go outside, you can reach temperatures that could be between 120 Kelvin and 395 Kelvin. So from very cold to quite warm. And this changes conditions for welding. So we know the physics of welding quite well. We've been doing this for more than 100 years, and there is a lot of models and knowledge on this. Once you get to space, these changing conditions, how they are going to affect the physics. We know the equations, and we know we can go there and make gravity zero, pressure zero. The problem is all the models we have been calibrated and developed based on on-air experiments. So we need to do experiments on space to make sure we can recalibrate our models and our knowledge correctly, then we can do this work safely. But welding in space is not new. This is, I'm not going to go in detail, but this is like what has been done on welding in space over the years. And you realize this starts back on the mid-60s, when the Russians did the very first parabolic flight on the Balkan program. Later on, they actually did flight experiments to orbit. The very first American in space well actually happened in '73. And this was as the Skylab. So you are younger, not me. You don't even know what Skylab is. We have several space stations. Skylab was one of the first, not the very first, because we have the Soyuz by the Russians and the Mir. But in '73, very first time US did an experiment of welding in space, electron beam welding. And guess what? Almost the last one that we did. More recently, we planned experiment, international one in '99. Even some of the components were flown, never actually realized. While we were doing that, the Russians were doing a very good job. They even had an astronaut in '84 going out in space on a walk, and she welded. It was a woman. She welded on space with a handheld tool. More recently, there is more activity in US and Europe. This is our experiment, the one we're going to be presenting, where we're building this and doing parabolic flights. NASA, based on this, is developing what they call the NASA Dixman. This is most likely going to the space station by the end of this year or next one, where they're going to put it outside the space station and do some laser welding as well. And you see here the lunar weld we're working on, we're going to be presenting. So a lot of work in the middle. Japanese also was very active on the late '90s. So we are not the first ones, but most of the previous work was all on electron beam welding. Laser has gone a big way. I mean, it has improved the technology a lot, especially the energy efficiency. Therefore, NASA wanted us to look into this, and that's where we have been working. A little bit on history. So we done plasma welding, electron beam welding, gas metal welding. The Russians on '69. Electron beam welding, the Americans on the Skylab in '73, as I mentioned. Second experiment canceled. Think Orbital just flew a rocket in '24 that just went to low orbit. Did electron beam weld. This is some of the experiments here. Laser beam welding, University of Osaka did some parabolic work on the past. The ISS with the European Space Agency, they flew to the space station a machine to do laser-based additive. They are finishing this experiment and what we're doing. In friction stir welding, Chinese university, Shangyao Tong University, they are doing some preliminary studies to use friction stir welding in space. There is also a huge company thinking about doing friction stir welding in space. So different technologies, different things. So technologies have been used, okay? Prior research has established, so we know some things already about welding in space. We know the geometry is very similar. What we call the heat affected zone, the region around the weld that gets hot and changes, is about the same. We have more porosity. We have some cracking that is not fully understood, and we have some difference in microstructure. There are a bunch of unanswered questions, okay? So what is the influence of microgravity and vacuum on extreme temperatures on the performance and quality of these welds, okay? Why the microstructure looks different from some of these welds that were done many years back? What is the allowable mechanical performance needed on these joints? And this is a very good point, because when we design things for space, we design them to withstand the launch, because the loads on space are normally very low, okay? And finally, this is important as well, is how these techniques are going to affect humans. When you do electron beam welding, you have X-rays being generated. This could be dangerous. You could also have reflections of laser welding. So this is also something that needs to be addressed. What we have done at Ohio State, okay, we're working, developing workforce. We develop an instrument that Kaue and John are going to explain in more detail, put it on a parabolic flight and get use of that to get low gravity effect. We collect a lot of data, okay? And we are working on analyzing the welds to understand the weldability of different alloys, aluminum, stainless steel, and titanium. And we're also working on modeling, using models to reproduce what we saw so we better understand, okay? This is the instrumentation we developed. We have this huge box. We have all these systems to move our systems. Laser comes in, and we make, this is an example of weld made here on low vacuum condition. This is an example of cross-section of the weld. Remember, this goes on a plane, and then we're doing these experiments where we're having low gravity under vacuum, also under control temperature. Okay, this is how these parabolic flights go along. Okay, in these systems, we have like 10 to 20 seconds of microgravity. The machines run by themselves, but we are there to help the machine make the job. We don't do parabolic flights. We have gone to the point where we have even built very small pressure vessels. These welds were made of microgravity. This is how the data looks like. So we get information about gravity, information about pressure, temperature, okay? We're collecting all this information that I'm listing here, all different ones, geometries, and also among them, video. We do thermal video, we do regular video, and we are doing now high-speed video as well. We haven't flown yet with the high-speed video camera, but we'll soon. Just a taste or a peek of data. You see, this is the sputter. When we're welding, sometimes metal start flying, and the trajectory of these particles changes because of gravity. So this is nice to see happening. Other thing is, we see that the porosity, in this case on stainless steel, changes, okay? It actually changes different between different materials and different gravity levels. These red dots in here are the pores that we are seeing during the gravity, microgravity experiments. Just to summarize, when we go from ground to lunar gravity, we had a reduction of almost 40% on the total volume of porosity. When we went from ground to microgravity, it's almost 80% reduction of porosity. Guess what? We don't really understand why this happened. And it actually just changed for other materials. So that's why these studies are needed. We have already some theories how this could be made, okay? We are doing laser, pulse laser, and this solidifies very fast, how these bubbles move on space. We're writing on these conditions, we're writing the papers on that. This is how some of these wells look like. They look slightly different, depends on the condition you're doing. You understand how the microstructure changes. And one of the things is we've seen grain size difference, aspect ratio of our grains difference as well. We are just scratching the surface why these things are happening and how we can control. Good thing is we build instrumentation, we have flown with it, we can reproduce all the conditions of space. Next step is we're going to do more parabolic flights, but we need to put a complex experiment like this one on low orbit, and we're working to put this together. So at this point, I'm going to stop talking, doing this introduction, and I'll let now Kaue talk a little bit more about the specific experiments we have performed. Thank you very much. Okay. You're there?
Yes, this was covering a little bit of that. There we go. So Let's go next slide here.
Introduce yourself, Kaue.
So my name is Kaue. I took some notes here to remind myself. I was teaching class right before this presentation. So I am a research scientist here at Ohio State University. I work with welding since I was an undergrad. It's been like several years in this field. I worked with different processes. And then I know that most of you probably are not from the welding field, so I promise I will try to talk more in a higher level language right here. And then if you guys want to go deeper, we can discuss during the Q&A session later on. So our group basically works with all kind of material joining here at Ohio State University, but arc welding is the most used one. And I want to make this transition from Professor Antonio talk about the welding space to why we are applying high-speed videos for this project and what we want to understand. So I want to start from the basics. So if you guys ever saw an arc welding before, this is an example of an arc welding. Using like a regular smartphone or even by eye, when you're looking to the welding, for example, using a face shield, welding shield, for example, you won't see much, right? You're gonna see that very bright region like this one, and then you have to understand what type of phenomena is happening behind that brightness that the arc is emitting. So basically, these type of things, there are phenomena happening during that process that can range from the microsecond range up to conditions where we can capture by naked eye what's going on, for example, the spatters. But when we talk about how the metallic transfer and how the molten pool is flowing inside it, things can happen very fast. And then in this process here, what we are seeing is basically an ionized gas that is forming this plasma, and this plasma emits light basically through the whole aspect range of of wavelength. So that's why we have UV, visible and infrared emissions, and then we're not able to, with regular techniques, to have a clear vision of what's going on in dynamic, what's hidden behind that metallic vapor that's going on in the plasma itself. So we have to have a combination of some illumination system with very fast, high-speed cameras and filters to achieve a better vision. So I'm pretty sure John, who's going to talk next, and Saba as well, will talk better about or deeper into the physics behind the arc visual or the welding visualization. But that's the message we want to show you here. So, and then everything started with arc welding, right? Before, so our experience was first applied to arc welding, how we can use high-speed techniques to improve and engineer welding processes much better. And then these are high-speed videos of arc welding processes where we go from a very low power condition with instabilities up to transitioning into conditions with a higher power, for example, where we achieve different metallic transfers condition. This changes totally how the welding resolves and how the microstructure evolves during the process as well. So during this thermal cycle. So using high-speed cameras was basically the solution that we found to apply to the welding space project in order to have a visualization of what's going on based on our knowledge acquired before in arc welding examples as presented in here. So this is another example of knowledge we had in arc welding that was transferred to this welding space project, where we were looking into engineering a much more efficient welding process for oil and gas repairs at that time. And then only without using high-speed camera techniques, we couldn't basically fully optimize and understand the phenomena behind the way the material was melting during the welding processes. So with the high-speed application technique, we were able to engineer this process and achieve, for example, in that case, over 900% increase in productivity and reduction in time for repairs in the oil and gas industry. So this is an example of the powerful tool that it is, that high-speed video is for this welding application. So this another example here shows a welding condition as well that was done during this arc welding project, where we basically were able to verify phenomena that are happening at very, very fast speed. And we could understand why we were able to achieve that much more efficient, 900% more efficient process at that time, why that process was happening in that way, why we could achieve such efficiency looking into the process using high-speed techniques. So these are very tiny micro arcs forming along the molten zone for the filler metal, and then this contributes to increase the melting rate for the material and make it more efficient. So all this knowledge was acquired, and then we translated this into the welding space project. So the goal of it was, in addition to understand the physics that I mentioned to you, what's going on with the molten pool, and then understand later on why a deeper penetration happens, or why the morphology changes, right? So we applied the high-speed cameras. So this is also, as Antonio mentioned before, our idea is to build models on Earth that we can later on reduce the amount of experimentation in open space, right, to understand the weld. But these models are calibrated, as he said, based on ground tests or Earth experiments, right? So this is a fluid flow modeling that we built so far, that we can simulate Earth condition and low gravity and understand how the fluid flow is going to solidify and the dynamic of the molten pool. So for those calibrations, we go back here. For those calibrations, we have to have such a technique that can assist us to validate the models in terms of solidification rate and the molten pool fluidity as well. So this is where the high speed enters in this project, right? So these are very fast laser pulsed welding applied to space. To have an idea, they last for microseconds, and the solidification rate for these molten pools, they can achieve up to 1 meter per second, which is so fast that we have to have a technology that help us in calibrate these models and understand the whole process dynamics. So now I'm going to pass the ball to John. He's going to talk about some specific results from the project.
Hello, my name is John Cicenas. I am a first-year honors engineering student at The Ohio State University. I joined the Ramirez group with Kaue and Dr. Ramirez about 2 years ago now as a high school intern, and I've been working here ever since. And I am the main person who uses the high-speed cameras and tries to implement them into these projects. So to start off, we're going to talk about high-speed video integration into the project. Now, high-speed video is not very easy to get when you're looking at a vacuum chamber, because there's very limited viewports here. So about 2, maybe 3 viewports that we can use to see into the chamber to keep that high vacuum. So we have to make sure the laser illumination system and the camera are able to see into these. And the idea behind recording this is we want to record orthogonally to the weld so we can see like the fluid flow and what's going on in the melt pool for model calibration. But like I said, there's a lot of challenges recording this. So first of all, the weld diameter is tiny, tiny, tiny. Laser welds with this spot size that we use range from maybe 0.5 millimeter to 2 millimeters. And in combination with the other issue, which is the 20-inch distance from weld to the viewport, which we use to look into it, creates a type of condition where we basically have to have a long range microscope to see really what's going on. So I will explain that in a little bit, but yeah, you're unable to place the camera or any optics into the chamber at all, just because the high vacuum will mess with how the camera works and will cause it to overheat and things like that. So for materials that we used the Phantom BEO 1310S high-speed camera. We have our laser illumination system here, some other like smaller setup things. Our vacuum chamber goes down to 10 to the -6 torr, which is very, very low pressure. That is considered high vacuum. And then, yeah, 1.5 kilowatt max output laser. So, yeah. So to solve the magnification and distance issue, we use some special optics here. So running the calculations for focal length, we wanted to target a 432 millimeter effective focal length. So as it turns out, this is quite hard to do with our minimum distance of 20 inches. You can get a higher focal length if your minimum distance away from the thing you want to view is farther. It comes down to some equations that I won't explain, but basically it's very hard to get this effective focal length. But using some optics here, Nikon Micro Nikkor 200 millimeter f-4 aperture macro lens and our 2x teleconverter, we were able to up our focal length to 400 millimeters, which is close enough to get what we need for our project. And then we also used some other optics that weren't vacuum specific to test our laser conditions, which I'll explain here in a little bit. So first, we did terrestrial welds. So we have a laser lab that we run for other projects besides this. And then we have our welding in space lab. So we started off with the laser lab to try and dial in the parameters that are extraneous to the laser parameter. So the idea is we keep the same laser parameters as we have under vacuum and test our conditions relating to the camera and the optics under terrestrial conditions. And then, of course, the vacuum welds, we get data related to vacuum. So for terrestrial welds, there are a bunch of parameters we had to account for. So frames per second. So what frame per second would we need to get optimal data for our model calibration, our resolution, our exposure time, or how much light is exposed to each frame after it occurs, our aperture opening, which is more to do with the lighting, our laser illumination incidence angle, which is the angle that the laser is pointing towards the viewpiece at. And then, of course, laser synchronization and some other stuff here. I believe Saba will talk more about the laser synchronization and illumination, but yeah. So here's a short little piece on the synchronization. The camera runs super fast, and we need a super fast laser to basically pulse whenever the camera exposes. And then so here's some what we did, I guess. F-sync signal to sync with the laser, and then a recording signal to start recording, and then the camera will start triggering on laser exposure, basically. So for terrestrial welds, we used our 6 kilowatt max power fiber laser. We simulated that 20-inch distance, and we had a coaxial lighting arrangement instead of the, I guess, a cross lighting. I don't know how to describe it, like a cross lighting arrangement we had earlier. And then we had a 50-degree camera angle to try and get as orthogonally as possible to the melt pool. So here's kind of what it looks like for our terrestrial welds. And then for our methodology under vacuum, we decided 24,000 FPS would be best to find our model. And then we had to vary our exposure time and aperture because turns out across the vacuum chamber, it's way different compared to just our terrestrial welds. And I'll explain that. We ended up at a 25-inch distance from lens to weld, 60-degree camera angle, and then, yeah, the laser on the opposite side of the chamber compared to the high-speed camera. So here's the data. So here's our welds. These are terrestrial welds. So the left was our first test weld just to make sure the parameters were working. And then on the right, we have the exact parameters of the vacuum conditions, just not in the vacuum lab. So this is our pulsed laser welding. And here you can see the fluid flow. So yeah. Now we go to the vacuum. This is what the results look like under vacuum here. So as you can see, it's way, way grainier than what we had hoped for. And we messed around with the exposure time and aperture too, to try and get the best results. But because of how the viewport works and some other things, yeah, the quality didn't turn out as good as we'd hoped, but it is still enough data to calibrate our models. So one of the key things we're looking at when calibrating our models is the spatter. So you can see here at the start of this video, there's some sort of explosion or like spatter explosion that happens at the very start, which is very weird compared to what we know for terrestrial conditions and what our models have predicted. Our models have predicted spatter that is not like this kind of instant explosion here. It's more of a slower kind of through the process thing. So yeah, here's a wider view of it. So it looks pretty crazy. And yeah. So another thing that we find interesting about this laser beam welding under microgravity is the height of the melt pool. You can see here, there's some shadow here, but the melt pool is very, very tall compared to welds under like regular terrestrial conditions. So we did some optical analysis here, and the bead heights are in the difference of like 500 microns or something from welding under vacuum compared to welding terrestrially, which is really weird considering this is an autogenous process, which means there's no filler metal. So yeah, this sort of raised, I guess, bead here is very weird. So then the other thing we wanted to look at for our model calibration was solidification rates. We are currently working on this. It's like a work in progress. So it utilizes MATLAB machine vision with some other image filters like a Gaussian filter, some other stuff, but it is still a work in progress. Yeah. So in the future, we have several things planned. So we want to get a parabolic flight in with the high-speed camera and laser illumination, but we're having some difficulties getting that set up right now, but it'll be in the future sometime. Another thing we're looking at is the Google Segment Analysis 2 model, which will help us with our solidification rates. I'm currently trying to shift it over from that MATLAB program to this SAM2 model to try and get better accuracy on how fast it's solidifying, so we can better calibrate our model. Another thing we're looking at is mirroring the lighting, because I'm sure you guys have seen in the videos, like the lighting, it's kind of not the best. We were messing around with the lighting parameters a lot in the chamber. So we're looking at maybe implementing a mirror system in there to bounce the laser off of. And then the last thing is doing the high-speed videos with the cooling system enacted. So in space, it's very, very cool. And warm too, I guess, but this also affects solidification rates and some other stuff regarding the weld. So yeah, that's about it for me. I'll have Dr. Ramirez come back in here and
Okay, thank you, John.
through our announcements.
So I will just say, I just want to make sure we acknowledge everybody who is involved in this work. It is our contact information, and you want to work with us, get involved in this research. We need a lot of people willing to work hard and smart people to help us. So please reach to us. We'll be happy. At this point, Maria and Saba, you can take over.
Thank you very much, Professor Antonio and team. Now we'll pass it over to Saba. So you are muted.
Sorry, can you hear me
Okay.
now? Yeah.
Yes, and now if you can share your screen,
Yes.
you can do it now.
Okay.
Excellent.
Is it working?
Yes, we can
Okay.
see you
Okay.
and we can see a presentation.
Okay. Hi everyone, I'm Saba Adabi and Field Application Engineer at Vision Research. I'm a tech. I have a degree in EE with experience in high-speed camera imaging, optical tomography, ultrasound imaging, and an interest in application-based software development as well. So welcome to our webinar, where now you know we are talking about combining ultra-fast illumination source and a synchronized high-speed camera to reveal and measure transient phenomena that happen too quickly to see. So I'm going to add some context to this technological advancement. Sorry, is it going, the team? Okay, yes. Okay, so many, as you know, many critical processes happen in microseconds to nanoseconds. The goal here is to convert too fast to see into actionable data, such as timing, velocity, stability, defect. A high-speed camera can provide that. Often people think the high-speed camera, high-speed imaging is only about frame rate, but it's also about exposure time. High-speed cameras often must use very short exposure times for different applications. However, there are some applications, same as welding, that you see that you need a laser. So mostly pulse lasers to deliver very short, very intense pulses. So your image become illumination limited rather than exposure limited. And also motion blur is minimized. So most of them, most of these lasers are being single wavelength, what we call monochromatic, which by that you could in some application filter out the unwanted signal by enabling a narrowband filter on the camera around specific wavelengths. For example, here around 808 nanometer to reject broadband arc or glue and keep mostly the laser illuminated image content. High-speed camera are paired with short pulse, mid or high power lasers, enabling accurate measurement in different applications, such as particle image velocimetry or welding. Welding, as you know, for the particle image velocimetry, they are offering sharp particle images for correlation, or in laser Schlieren imaging, where one could obtain high contrast visualization of density gradients. Also, they are being used in spray analysis and energetic event to image energetic event like ballistic to get clear imaging of extremely fast, bright events. And also to this end, as you saw in previous presentation, one should also consider other optics like lens selection based on the application. Here you could see some examples that how high-speed cameras and lasers work together to capture event. For example, they are being used in additive manufacturing, welding process similar to what you saw, or like for Schlieren imaging and particle image velocimetry. Okay, now let's little bit talk about how the camera and laser communicate to each other. So the laser and camera communicate via TTL logic through BNC cables. Let's go through some key terms here. On the camera side, there is normally a strobe. Oh, sorry. There is normally a strobe, which is a pulse generated by the camera synchronous with the sample rate. For example, in phantom camera, this signal remains low for the duration of exposure or integration. There are other signals that it can be used, such as the camera internal frame rate generator, the crystal oscillator, which outputs a pulse on that signal to initiate acquisition of the image frame. An important thing is that people should know is in high-speed camera world, a trigger is typically the event that defines time zero relative to the circular buffer in its memory pipeline. So on the laser side, we have the trigger. We have the trigger input, which needs to be wired to the camera input-output port, and then the laser controller. The laser controller, which outputs pulses on each trigger with a user-defined delay and pulse width, enabling precise placement of illumination with the camera exposure. Then there is repetition rate, which basically are the pulses per second, and then the duty cycle. Knowing the pulse width of laser is how long each pulse stays on. The duty cycle is the fraction of each period that pulse is on. Laser and camera can be synchronized in primary and secondary architecture. So one of them will be as your master clock, or they can be run in some cases by an external clock. So note that your repetition, the repetition rate of laser system is set based on the camera frame rate for like consistent illumination, and laser pulse width set based on the camera exposure time. So you could, in some cases, program the pattern if needed. And always oscilloscope is your best friend to monitor these signals. To conclude, so the first step is pick your primary master clock in a laser camera if you are trying to freeze the motion inside the exposure. The second step is setting the laser pulse timing. Set pulse width short enough to freeze the motion. Remember, these illumination lasers are built for very short pulses and high repetition rate. So adjust the delays if needed, so the pulse is centered or placed wherever you want inside the exposure window. From the camera strobe, which is your exposure indicator, or if you're using the rest of the camera input-output, such as f-sync reading or recording signal, probe them with an oscilloscope. Also check the laser pulse. You could monitor it with a photodiode as well and confirm the laser pulse is inside this strobe exposure. Now you can happily do the beyond invisible imaging, and above all of them, don't forget most of these illumination sources are class 3B or class 4 lasers. So put on your goggles and use the appropriate interlocks and other ideas. Thank you so much for listening to our presentation. This is two more examples from particle image velocimetry and laser-based, and also the welding process. Thank you.
Thank you so much, Saba. Yes, because we couldn't see you. Okay, great. Thank you so much, Saba. Thank you so much to the welding engineer team at the Ohio State University. If you have any questions, please feel free to just type it on the chat and we can go over those questions. In the meantime, I do have a couple of questions for the team. So number one, you were telling us about gathering a lot of data points, right? A lot of data points for this incredible research. For someone who is about to start learning or they have any type of experiment related with welding in aerospace, what are like the top 3 type data that you recommend that they need to go and start with those 3 points? Because you guys discussed a lot about like the air condition, low gravity, but if it's someone is new, what are like those top 3 data points that you would recommend for them to start looking for welding in aerospace?
That question is for us, Maria?
Yeah.
Okay, so for space, remember there are 3 conditions that change: pressure, gravity, and temperature. So depends on the phenomena you are studying. Some of them are more important, have a much larger effect than others. So for example, for solidification, the gravity plays a very important role that is not very well understood. So in solidification, that's a key one. If you're looking, for example, at engineeringly just making the weld, gravity is important, but I will say maybe pressure, the vacuum, is more relevant in that case. So it depends on what you are trying to study and the question you are trying to answer. A few things will change a little bit.
Okay, perfect. Thank you. I do see another question in the chat. How does vibration affect the data, and will there be value added by being able to get vibration data from the high-speed videos?
That's a very good question, by the way. Yes, you're right. When we're doing these experiments, we are sitting on a very old plane, older than you will feel comfortable flying on. Okay, and so it vibrates, and the plane is taken to its limit. When they make these parabolas, not regular commercial planes cannot take many of these parabolas. So what happens is it vibrates a lot. So the whole thing is vibrating, and that's the jigger in our gravity data. All this noise is vibration. So we have the data, we can come back and correlate. We haven't done high-speed camera during the flights yet. We may be able to correlate. It may look awful because if we don't attach the camera very well, then the whole thing is going to be shaking too much. So good point. That's something we'll have to look after. I keep pointing there. our camera will have to have the less possible mass, so it's less affected by vibration, by this vibration.
And I want to add to what Antonio said there. The reason we picked the Phantom VO 1310S is because it is lightweight and compact for if we want to integrate it into that, parabolic flight. So, yeah.
Okay,
Thank you.
perfect.
Just
Okay,
one thing that I can add to this question is like, if you wanted to get also like the vibration, because it's like a high-speed camera, so the temporal resolution is like very closely spaced, so you could get the vibration using the frequency, inverse of the frequency, right? Thank you.
So there is a question there that I think is for you guys, Maria and Saba. It's about like price point and things like that. Not my field.
Okay, yes, and we will take that offline, Wesley, for price discussion. And like Professor Antonio, I think that we might want to have another session when you go into a flight, and then you can share the results after the flight. But I do have another question here. Any guess on why the difference between weld, melt, height between the two environments? Does it have any obviously discernible changes in mechanical stability to a terrestrial?
So I actually just talked to Professor Ramirez about this before our presentation because I thought it was pretty interesting. And basically the consensus is we have no clue. We don't really know. At first, thought, could think maybe there's no pressure, so maybe it's changing the density, but the fluid is incompressible, so it doesn't have to do with pressure. So yeah, we really don't know.
We just realized this recently. We don't have an idea yet. I just had the conversation with John, about this. So we'll have to look into this. We have no idea yet. That's what science is. That's what makes our job so fascinating. Is we have more questions than answers, and that's our job, is choose the right questions to answer.
One thing we verified comparing, for example, the flight samples versus terrestrial was in the keyhole collapse. So that's why when Antonio presented that theory we have so far, why we have the differences in the pore shape and volume. We think that there is difference in the way that the welding keyhole will collapse when you compare the two different conditions. That might be one of the pathways to kind of try to answer this question, but yeah, still are investigating.
Okay, well, thank you. See another, but this is more like a comment for Saba, for us. Can the camera be integrated for a spectral analysis? You're muted, Saba.
Yes. Yes. We also already done this, and we have a white paper on using our camera as a to get the information of the spectral information. Maria could send the information, or I can if you just email us. And then on the vibration part, we have a software which just get the its input is the cine file, or any other file, cine file specifically, and it can output the vibration information. The name of the software is PCA. If any of you use Phantom camera and didn't use that, so you could just download it from our website. It gives you from the cine file, it can output for you the vibration information if you need it.
Okay, great. I think that this is not a question, but it's right, using RDI software, you can gather FFT waveforms using Phantom camera, so you don't need for a new equipment.
Yes.
Okay, perfect. Just right on time. Thank you very much again, everyone, for joining us today. Thank you to the team at The Ohio State University that we have the pleasure to work with in this experiment, and also to Saba, who is our applications engineer for the Phantom team. So after this webinar, we are going to be sending the recording. If you want to revisit, hear more about the research, and also we are going to be sending you some white papers for references. So thank you so much again for your time. And we are going to be running monthly webinars with different topics related to high-speed imaging. So stay tuned in our different social media channels, and have a wonderful rest of the week. Thank you, everyone.
Okay, thank you.
Thank you.
Thank you.
Thank you for inviting us.